Hello and welcome to our video on the unit circle. And we should say that the unit circle is very useful in trigonometry. It allows us to deal with the sine, cosine, and tangent in a really nice way. And I think you'll see that as we go through these videos. Now the unit circle has a center at 0, 0 on the x and y axis. So we have our x and our y-axis, and there's the point 0, 0. It's the origin, and that's where I'm putting my unit circle. A great feature of the unit circle, and this is probably what makes everything so easy, is that the radius of the circle is 1. So anywhere I go on this circle, up here, down here, anywhere from the center to the circle is 1, right? That's what a radius means. So the radius is always 1. So this has a length of 1, so does this, right? And that is such an important feature of the unit circle, one we're going to come back to. So the radius is 1. Just write that down. And that means the diameter is 2. If you remember, the diameter is just twice as long as our circle, right? It goes from one end of the circle all the way to the other. So that's really just 2 radiuses, and a diameter is 2. So that's really basic features of the unit circle, and the unit circle is really important, and here's why. Here's one of the reasons why. We've talked about in other videos that if we want to deal with sine or cosine or tangent, what we can do is look at a right triangle, and we would have the right angle, and then we'd have an angle theta, and we'd want to know, well, if the sine of theta is going to be equal to, well, it's going to be equal to the opposite side over the hypotenuse, and that works out nicely. Sine's opposite over hypotenuse. The cosine of theta is the adjacent over the hypotenuse, the adjacent side relative to the angle over the hypotenuse, and the tangent of theta is just equal to the opposite over, I'm going to put divide here because I think I'm running out of room, the opposite divided by the adjacent side. And this goes back. We have this nice acronym, Sohcahtoa, to help us remember these ratios. Otherwise, I think it's pretty difficult to do. This acronym seems to work pretty well. So what's the problem with this? Well, what if I asked you to find the sine of a bigger angle or the cosine of a bigger angle? For example, what if I said I want to know the sine of 720 degrees? Well, the problem with the triangle is that we can't use the triangle to answer this question because we can't have a triangle with 720 degrees. And I guess we could construct triangles that somehow revolve around this principle, but it seems just overly complicated. And that's where the unit circle comes in. It can deal with angles like 720 degrees, or what if I wanted to know the sine or cosine of negative 30 degrees? How would I deal with that in a triangle? What if I wanted to know the sine of 90 degrees? Well, you might say, well, couldn't we use this 90-degree angle? Well, no, because this 90-degree angle is the angle that's across from the hypotenuse, and the whole ratio system of the sine, cosine, and tangent is based on the fact that the angle you choose is not this angle, right? So this has a whole new ratio structure. So the sine of 90 would mean that theta is 90 degrees. And let's talk about that for a moment. We can't have that angle being 90 degrees. If we already have an angle in our right triangle that's 90 degrees, if this angle over here, theta, is 90 degrees, look at our shape. Oops. Look at our shape. This is not a triangle anymore. This is some kind of other shape, right? If I even wanted to bring these two to a point, we'd have some kind of house thing, but now we have all these other angles, and this is no longer a triangle. So how do we answer the sine of 90 degrees? Or what about the sine of 0 degrees? Or the sine of 180 degrees? All of these things can't be built into a triangle. You can't have a 0-degree angle in a triangle, right? If we had a line right here and said, well, a 0-degree angle wouldn't go up or down, so how would I create my triangle? As soon as I make a triangle, I create an angle. So all of these things right here, I create an angle above 0 degrees, or above 180, which is just a straight line. So we need a way of dealing with all of these things, and that's the unit circle. And I hope that as we go through some unit circle examples, we become so comfortable with it that maybe you even prefer the unit circle to using right triangles. So let's look at some basic applications, and then in other videos we'll actually go through the details of the circle. Okay, so let me redraw our unit circle. That's the unit circle with a radius of 1. There's my y-axis, and this is my x-axis. So let's just deal with one of the questions I just asked, which was, how do you find the sine of 30 degrees? The sine of 30 degrees. The way we deal with that in the unit circle, we draw a line, right, from the origin to the circle, and you can think about how this angle right here would represent 30 degrees. That's our angle measure. So when we're measuring angles in a unit circle, I think of them as being measured from the x-axis. So here we go up from the x-axis 30 degrees, and we draw this line, and that's a radius. So that equals 1, right? In the unit circle, the radius is equal to 1. And in the unit circle, what you're really examining is this point right here. We want to know what does this point equal to. So to help us do that, we drop a line from the point to the x-axis, and then we connect these 2 points right here. And what we're doing now is creating a right triangle that can be moved, right? If you can imagine this right triangle, it can be in different spots in the unit circle, but it will allow us to deal with other angles. So in the unit circle, we have right triangles. And we want to know, well, what is the sine of 30 degrees? So that's our angle. That's our 30-degree angle right there. And we want to know what's the sine of that. Well, we still have our acronym Sohcahtoa. And that still applies because now we've drawn a right triangle in the unit circle. So we can use what we know, that the sine is equal to, we have so it's equal to the opposite side over the hypotenuse. And the opposite side is just right here. This is the opposite. And we should think about what that means. Well, the opposite is the height of this point. And that's going to be whatever our y value is. In coordinate geometry, if I go up to reach a point, that's my height. That's y. And that's just where the point is over here. So the opposite side, the length of this triangle right here, is just going to be equal to my y value. And the sine is equal to the y value over the hypotenuse, right? The opposite over the hypotenuse. So the sine of 30 degrees is going to be equal to y over the hypotenuse. But the hypotenuse, let me rewrite it. You can see it right here. The hypotenuse is just 1. This is a unit circle. So the sine of 30 is equal to the y value, the opposite side, over 1. So the sine of 30 is going to be equal to our y value. Now we don't know what our y value is, but let's just generalize and say that the sine of our angle, 30 degrees, is going to be equal to just the y value. And that's really nice, because in a unit circle, if I want to know what the sine of an angle is, all I have to do is look at the y value of the coordinate on the circle. And let's just step back a moment and think about the cosine of an angle. Well, the cosine is equal to the adjacent side over the hypotenuse. And already we might see that's kind of nice because, again, we're dealing with the hypotenuse, which is just 1. So our adjacent side is right here on the triangle. This is the adjacent to the angle, 30 degrees. Adjacent, ADJ, adjacent. And that, if you notice, is just the x distance. So the adjacent side on your triangle is just equal to the x distance of the coordinate. So the sine of theta is equal to the x value over 1. That's the length of the hypotenuse, adjacent x over hypotenuse 1, and that's just x. So if you want to know the cosine of the angle in a unit circle, all you have to do is look at the x value. So the cosine of theta is equal to x, and the sine of theta is equal to the y value. And that seems pretty nice. So if you are given the point, or if you can find that point, you could find cosine and sine of an angle. What about tangent? Let's just deal with that. Tangent of theta is equal to the opposite side over the adjacent. Well, the opposite side of theta, here's theta, the opposite side is just y, and the adjacent side is just x, so it's y over x. So the tangent just looks at these two values in the coordinate and places one over the other. It's y over x, and that's tangent. And in a way, that's just and this is often overlooked, if sine of theta is y and cosine of theta is x, and the tangent of theta is y over x, then the tangent of theta is also the ratio of sine of theta over cosine of theta, y over x. So you can think of tangent as a ratio of sine to cosine. And that's going to lead us to some interesting properties. And in the next video, I think we'll answer the details of how to find the sine of 30, and that will reveal, I think, some interesting properties of the circle.